cosm. Whoosh.
Picture this. You're standing on a world that's been dead for billions of years. The wind howls past you at speeds that would tear apart a building on Earth, yet you barely feel it. The air is so thin it's practically a vacuum. Above you, the sky glows a butterscotch hue, nothing like the blue you've known your entire life. And beneath your feet, red dust stretches to the horizon, hiding secrets that could rewrite everything we thought we knew about life in the universe. Welcome to Mars, the red planet, our cosmic neighbor, and possibly the greatest mystery humanity has ever encountered. You see, Mars isn't just another rock orbiting the sun. It's a time capsule, a frozen archive of planetary history. And the more we explore it, the more we realize that the story it's telling us is far stranger than we ever imagined. Let me take you on a journey, not just across space, but through time, through evidence, through mysteries so profound, they'll make you question what you thought you knew about our place in the cosmos. Here's what we know. 4.5 billion years ago, when our solar system was young and violent, Mars was a very different world. Rivers carved through its surface, lakes pooled in its craters, an ocean, potentially covering a third of the planet, lapped against ancient shores. The atmosphere was thick enough to hold liquid water, warm enough to sustain it. Mars was wet. Mars was warm. Mars was, by all measures we understand, habitable. Then something catastrophic happened. The planet's magnetic field collapsed. Without that protective shield, solar wind stripped away the atmosphere like pages torn from a book. The water evaporated into space or froze into the ground. The rivers dried up. The ocean vanished. Mars transformed from a potentially living world into the desiccated wasteland we see today. But here's where it gets interesting. That transformation didn't happen overnight. It took hundreds of millions of years, maybe longer, which means there was a window, a vast expanse of time when Mars could have harbored life. Not just microbial life hiding in rocks, but potentially complex ecosystems thriving in those ancient seas. And if life emerged on Mars during that window, where did it go? Did it die out completely? Or did it adapt? Did it burrow deep underground, where liquid water still exists today in subsurface aquifers? Did it retreat into caves, into the depths of the Martian crust, where it might still survive, waiting to be discovered? That's not science fiction. That's a legitimate scientific hypothesis based on what we've observed. Now, let me tell you about Gale Crater. This is where NASA's Curiosity rover has been exploring since 2012. It's not just any crater. It's a 96-mile wide impact basin that was once home to a lake. We know this because Curiosity has been studying the sedimentary layers exposed on the crater's central peak, Mount Sharp. These layers are like pages in a history book, each one representing a different chapter in Mars's climatic evolution. And what Curiosity found in these layers is extraordinary. Organic molecules, complex carbon compounds, the building blocks of life as we know it. Now, before you get too excited, organic molecules don't necessarily mean life. They can form through non-biological processes. Comets and meteorites deliver organic compounds to planetary surfaces all the time. But here's the thing. The organic molecules Curiosity detected aren't just scattered randomly across the surface. They're concentrated in specific sedimentary layers formed when liquid water was present. They're preserved in rocks that were once mudstones at the bottom of a lake. That's exactly where you'd expect to find biological organic compounds if life existed in that ancient lake. Curiosity also detected methane. This is huge. On Earth, 95% of atmospheric methane is produced by living organisms. Bacteria in swamps, in the guts of animals, in soil, they all release methane as a metabolic byproduct. The remaining 5% comes from geological processes, like volcanic activity or chemical reactions in hydrothermal systems. Mars has been volcanically dead for hundreds of millions of years. So where's the methane coming from? and it's not a constant presence. The methane concentration in Mars's atmosphere fluctuates. Sometimes it spikes dramatically, then drops back down. Curiosity detected a spike in 2013 that was 10 times higher than background levels. It persisted for about 60 Martian days, then vanished. That pattern of episodic release is difficult to explain through purely geological processes. But you know what does produce methane in episodic bursts? Microorganisms, specifically methanogens, a type of archaea that thrives in anaerobic environments. Could there be colonies of methanogens living beneath the Martian surface, periodically releasing methane into the atmosphere? It's possible. In fact, it's one of the most compelling explanations we have. But let's go deeper. Literally. In 2018, the European Space Agency's Mars Express orbiter detected something extraordinary using ground-penetrating radar. About a mile beneath the southern polar ice cap, there's a lake. A liquid water lake. It's about 12 miles across, filled with extremely salty water that remains liquid despite the frigid temperatures because salt dramatically lowers water's freezing point. This isn't a hypothesis. This is a confirmed observation. There is liquid water on Mars right now. And where there's liquid water, especially in a stable, protected environment like a subsurface lake, there could be life. Think about Earth's subglacial lakes, like Lake Vostok in Antarctica. It's been sealed beneath 2 miles of ice for millions of years, completely isolated from the surface. And when scientists finally sampled it, they found life. Bacteria and other microorganisms thriving in that dark, cold, isolated environment. If life can exist in Lake Vostok, why not in Mars's subsurface lakes? But the mysteries don't stop there. They get stranger, much stranger. Let me tell you about Jezero Crater. This is where NASA's Perseverance rover is currently exploring. Like Gale Crater, Jezero was once home to a lake. But this wasn't just any lake. It was fed by rivers that carved deep channels through the surrounding terrain. You can still see the river delta, frozen in time, where sediment once flowed into the lake and deposited layers of mud and clay. Perseverance is specifically looking for signs of ancient microbial life in these delta deposits. And it's making discoveries that are, frankly, baffling. In one rock sample, Perseverance detected organic molecules alongside minerals that only form in the presence of water. But the concentration and diversity of these organic compounds are unlike anything we've seen before. They're complex, varied, and abundant. Some scientists are calling it the most promising evidence for ancient Martian life we've ever found. But we won't know for sure until those samples are returned to Earth. And that's the plan. Perseverance is collecting and caching rock samples that will eventually be retrieved by a future mission and brought back to Earth for detailed analysis in laboratories far more sophisticated than anything we can send to Mars. That sample return mission is scheduled for the 2030s. Until then, we're left with tantalizing hints, clues, pieces of a puzzle that's still being assembled. Now, let me tell you about something that's going to make your skin crawl. In 2008, the Phoenix lander was digging in the Martian Arctic when it found something unusual in the soil: perchlorate salts. These are highly reactive compounds that can act as a powerful oxidizer. On Earth, they're found in some of the driest deserts, and certain bacteria can actually metabolize them, using them as an energy source. But here's where it gets weird. The concentration of perchlorates in Martian soil is much higher than we'd expect from purely geological processes. Some researchers have hypothesized that biological activity could be responsible for enriching perchlorate levels in the soil. Even more intriguing, perchlorates can absorb moisture from the atmosphere, creating thin films of liquid brine even in Mars's frigid conditions. These brines could potentially support microbial life, providing tiny pockets of habitability in an otherwise hostile environment. There's a hypothesis, proposed by astrobiologist Dirk Schulze-Makuch, that Martian microbes might actually use perchlorates as a kind of antifreeze, incorporating them into their cellular chemistry to prevent freezing. If true, these organisms would be unlike anything on Earth. Alien life with completely different biochemistry, adapted to a world where water is scarce and temperatures plunge far below freezing. But wait, there's more. And this is where things get really unsettling. Remember those recurring slope lineae I mentioned? Let me tell you more about them. These are dark streaks that appear on Martian slopes during warm seasons, then fade during cold seasons. They were first spotted by the Mars Reconnaissance Orbiter in 2010, and they've been controversial ever since. Initially, scientists thought these streaks were caused by flowing water, briny seeps trickling down slopes when temperatures rose above the freezing point of salty water. That would be incredible because it would mean liquid water is flowing on Mars's surface right now, not just locked away underground. But subsequent analysis threw cold water on that idea. The streaks don't behave quite like water flows. They're more consistent with granular flows, like sand or dust sliding down slopes. However, and this is crucial, the debate isn't settled. Some researchers still believe water plays a role in forming these features, perhaps by temporarily lubricating the soil, triggering these flows. Others have suggested they could be caused by deliquescence, where perchlorate salts absorb atmospheric moisture and create tiny amounts of liquid brine that destabilizes the slope. The point is, we don't fully understand them. And anything we don't fully understand on Mars is potentially a window into something profound. Now let me tell you about Mars's moons, Phobos and Deimos. These two irregular chunks of rock orbit Mars in a way that's frankly bizarre. Phobos, the larger of the two, is only 14 miles across. It orbits Mars at an altitude of just 3,700 miles, closer to its planet than any other moon in the solar system. And it's getting closer. Tidal forces are gradually pulling Phobos toward Mars at a rate of about 6 feet per century. In about 50 million years, it will either crash into Mars or be torn apart by tidal forces, forming a ring around the planet. But here's the mystery. We don't know where Phobos and Deimos came from. They look like asteroids. Their composition is similar to carbonaceous chondrites, a type of primitive asteroid common in the outer solar system. The obvious explanation is that they're captured asteroids, snagged by Mars's gravity as they passed nearby. But the orbits don't support that hypothesis. Both moons orbit Mars in nearly circular, equatorial orbits. That's extremely unusual for captured objects, which typically have irregular, inclined orbits. Capturing even one asteroid into a near-circular equatorial orbit would be astronomically improbable. Capturing two defies statistical expectations. So what's the alternative? Some scientists think Phobos and Deimos formed from debris ejected when a massive impact struck Mars early in its history. That would explain their composition and orbits. But it creates another problem. Impact-generated moons should have more in common with the planet they orbit. Phobos and Deimos don't. Their composition is distinctly different from Martian rocks. There's a third hypothesis, and it's wild. What if Phobos and Deimos are remnants of a much larger moon that once orbited Mars? A moon that was shattered by an impact or tidal forces, leaving behind these two fragments. That would explain both the orbital characteristics and the unusual composition. But if that's true, where's the rest of the original moon? Could there be more fragments we haven't discovered yet? Could there be debris scattered across Mars's surface, perhaps buried under the regolith? We don't know, but there are plans to find out. Japan's space agency, JAXA, is developing the Martian Moons Exploration Mission, or MMX, which will visit Phobos, collect samples, and return them to Earth in 2029. Those samples could finally solve this mystery. Unless, of course, they create new mysteries, which, based on our track record with Mars, seems likely. Let me tell you about the face on Mars. Now, I know what you're thinking. You've heard about this. It's a rock formation that looks vaguely like a face in low-resolution images taken in the 1970s. It's been debunked. It's just pareidolia, our tendency to see faces in random patterns. And you're right. High-resolution images clearly show it's just a mesa eroded by wind and time. There's no alien monument on Mars. But here's the thing. The face on Mars isn't interesting because of what it turned out to be. It's interesting because of what it represents. It's a reminder that Mars has the power to fool us, to make us see what we want to see, to make us jump to conclusions based on incomplete data. And that's terrifying when you think about it, because we're still working with incomplete data. We've explored less than 1% of Mars's surface with rovers. The vast majority of the planet remains unexplored, known only through orbital imagery and remote sensing. What else is hidden out there? What other formations might we misinterpret? What signs of past or present life might we overlook because we don't know what we're looking for? Consider this. Every time we've sent more sophisticated instruments to Mars, we've discovered things that previous missions missed. Curiosity found organic molecules that earlier rovers couldn't detect. Perseverance is finding even more complex organics with its advanced instruments. Each generation of technology reveals a deeper layer of Mars's complexity. What will we discover with the next generation of rovers? With human explorers who can make real-time decisions and investigate interesting sites in ways robots can't. Now let me tell you about Mars's lost ocean. And I'm not talking about the ancient ocean that existed billions of years ago. I'm talking about what happened to all that water. Mars was once covered in water. Rivers, lakes, and an ocean that might have held more water than Earth's Atlantic Ocean. We can see the evidence everywhere. Valley networks carved by rivers, sedimentary layers deposited in ancient lakes, coastal features that mark the boundary of a long-vanished ocean. But where did all that water go? Some of it is still on Mars, frozen in the polar ice caps and trapped as ice in the soil. But that accounts for only a fraction of the water Mars once had. The rest escaped into space, stripped away by solar wind after Mars lost its magnetic field. Except we've calculated how much water should have been lost to space, and it doesn't add up. There's a significant amount of water missing, unaccounted for. Where is it? The leading hypothesis is that a substantial portion of Mars's ancient water is trapped underground. Deep underground, locked in minerals, frozen in ice layers, or even existing as liquid water in deep aquifers heated by residual geothermal energy. In 2018, scientists analyzing data from multiple Mars missions proposed that Mars might have an underground reservoir of liquid water stretching across the planet, hidden beneath the surface at depths where temperatures and pressures allow water to remain liquid despite the cold surface conditions. If that's true, we're talking about a potentially planet-wide subterranean ocean, a hidden biosphere, an entire ecosystem that might have evolved in isolation for billions of years, separate from the surface, protected from radiation and temperature extremes. Think about the implications. If there's life in this underground ocean, it would have had billions of years to evolve in complete darkness, feeding on chemical energy rather than sunlight. It might have developed completely different biological solutions to the challenges of survival. It might not even use DNA. It might have a biochemistry based on different molecules, different solvents, different energy sources. It would be truly alien life, not just Martian microbes that happen to live on a different planet, but life with a fundamentally different origin and evolutionary history from anything on Earth. And here's the terrifying part. We have no way of detecting it with current technology. Our rovers can only drill a few inches into the Martian surface. Our ground-penetrating radar can see structures deep underground, but it can't definitively identify biological signatures. We can hypothesize all we want about underground oceans and subterranean biospheres, but we can't confirm or deny their existence without sending missions specifically designed to drill deep into Mars and sample those environments. Those missions are being planned. NASA's Mars Life Explorer concept proposes a drilling mission that could reach depths of several kilometers, accessing those deep aquifers and searching for life where it's most likely to exist. But such missions are expensive, technologically challenging, and decades away from reality. Until then, we're left wondering, imagining, what's down there? Is Mars alive in ways we can't see from the surface? Let me tell you about Mars's atmosphere. It's thin, about 1% the density of Earth's atmosphere. It's mostly carbon dioxide, with traces of nitrogen and argon. Not breathable, not protective. Standing on Mars's surface without a spacesuit would kill you in seconds, not from lack of oxygen, though that would kill you eventually, but from the extreme low pressure. Your blood would literally boil in your veins. But here's the weird thing. Mars's atmosphere changes. Dramatically, seasonally. During Martian winter, carbon dioxide freezes out of the atmosphere and deposits as dry ice at the polar caps. This removes enough gas from the atmosphere that the overall atmospheric pressure drops by 25%. A quarter of the atmosphere literally falls out of the sky as snow. Then, when spring arrives, that dry ice sublimes back into gas, and the atmospheric pressure rises again.
Mars brette.
Its atmosphere expands and contracts with the seasons in a way that's completely alien to our experience on Earth. But there's something else. Something we noticed in the data from various Mars missions. The seasonal atmospheric changes don't quite match our models. There's more variability than we can explain through simple sublimation and deposition of carbon dioxide. Something else is exchanging gases with the atmosphere. Something we don't understand. Could be geological. Minerals that absorb and release gases as temperatures change. Could be physical. Subsurface ice that traps and releases atmospheric gases. Or, and this is where it gets speculative, it could be biological. If there's life beneath the surface, its metabolic processes could be affecting atmospheric composition in subtle ways we're only beginning to detect. We don't know, but the fact that we don't know is itself significant. Mars's atmosphere is trying to tell us something. We just haven't figured out how to listen properly yet. Now let me tell you about Martian dust storms. These aren't ordinary storms. They're planetary-scale monsters that can engulf the entire planet in a shroud of dust that blocks out the sun and rages for months. In 2018, a dust storm began in late May. Within a few weeks, it had grown to cover the entire planet. The opacity of the atmosphere increased so dramatically that Opportunity rover, which relied on solar panels for power, couldn't generate enough electricity to function. It shut down. And despite NASA's best efforts to reestablish contact, Opportunity never woke up. After 15 years of unprecedented exploration, a dust storm ended its mission. But here's the mystery. We don't fully understand how these global dust storms start or why they sometimes engulf the entire planet while other times they remain localized. We've observed Mars for decades, and these planet-encircling storms seem to follow a rough pattern, occurring roughly every 3 to 4 Martian years. But the triggers remain unclear. What causes a local storm to suddenly explode into a global phenomenon? Is it a cascade effect, where dust lifted into the atmosphere absorbs sunlight, heats the atmosphere, drives stronger winds, which lift more dust, creating a feedback loop? That's the prevailing theory, but it doesn't explain why some local storms trigger this cascade and others don't. And there's something else. During these global dust storms, strange atmospheric phenomena occur. Lightning, for instance. Mars doesn't have a magnetic field strong enough to protect against solar wind, and its atmosphere is too thin to generate the kind of electrical storms we see on Earth. Yet during major dust storms, we've detected radio emissions consistent with electrical discharges. Dust particles rubbing against each other can generate static electricity, and that electricity has to discharge somehow. But we've also detected radio emissions that don't fit the dust friction model. Brief, intense bursts of radio energy that some researchers think might be coming from beneath the surface. Could these be tectonic? Mars is supposed to be geologically dead, but maybe it's not as dead as we thought. Could there still be tectonic activity, perhaps triggered by the massive changes in atmospheric pressure during global dust storms? Or could these radio bursts have another source entirely? Natural electrical phenomena we don't understand? Something else? We don't know, and that uncertainty is unsettling. Let me tell you about Mars's volcanic history. The planet is home to the largest volcano in the solar system, Olympus Mons. This shield volcano towers 72,000 feet above the surrounding plains, nearly 3 times the height of Mount Everest. Its base covers an area roughly the size of Arizona. It's so massive that if you stood on its summit and looked toward the horizon, you wouldn't see the base of the volcano. It would be hidden beyond the planet's curvature. Olympus Mons is extinct, we think. It hasn't erupted in hundreds of millions of years. But here's the unsettling part. We don't know for certain that it's truly dead. Volcanic activity requires heat. On Earth, that heat comes from our planet's molten core and the decay of radioactive elements in the mantle. Mars is smaller than Earth, which means it cooled faster. By all accounts, its core should be solid, or at least mostly solid. There shouldn't be enough heat left to drive volcanic activity. But in 2012, researchers analyzing data from multiple Mars missions found evidence of relatively recent volcanic activity. By recent, I mean within the last 10 million years. That's practically yesterday in geological terms. They found lava flows in the Elysium Planitia region that show minimal weathering and cratering, suggesting they're extremely young. They found volcanic vents that haven't been buried by dust, which should have happened if they were truly ancient. And they found subtle seismic activity detected by InSight lander that might be consistent with magma movement deep beneath the surface. Is Mars still volcanically active? Could Olympus Mons erupt again? Probably not in our lifetimes or even in the next million years. But the possibility that Mars isn't as geologically dead as we thought raises profound questions. If there's still heat in Mars's interior, that heat could be melting ice, creating subsurface pockets of liquid water. Could be driving hydrothermal systems, like the deep-sea vents on Earth where life thrives in the absence of sunlight. It could be creating habitable environments deep beneath the surface, places where life might not just survive, but thrive. The InSight lander, which operated from 2018 to 2022, was specifically designed to study Mars's interior. It carried a seismometer that detected Marsquakes, tremors that provide clues about the planet's internal structure. Over its mission, InSight detected more than 1,300 Marsquakes, ranging from barely perceptible tremors to significant quakes that would register around magnitude 5 on Earth. What InSight discovered was shocking. Mars is more seismically active than expected. The planet experiences regular quakes, some of which originate from deep in the mantle. The pattern of seismic activity suggests that Mars's core might be partially molten, not fully solidified as previous models predicted. A partially molten core means Mars is warmer inside than we thought. It means there's more geological activity than we realized. It means conditions for life in the subsurface might be better than we dared hope. But it also means Mars is more unpredictable, more alive in a geological sense. And that raises uncomfortable questions about what we might trigger when we start drilling into Mars, when we establish human colonies, when we begin terraforming efforts. Will we inadvertently wake up something that's been dormant for millions of years? Now let me tell you about Mars's radiation environment. This is one of the biggest challenges for human exploration. Without a magnetic field and with only a thin atmosphere, Mars's surface is bombarded by cosmic rays and solar radiation at levels that would be lethal to humans over time. The Curiosity rover has been measuring radiation levels on Mars since 2012. The data is sobering. An astronaut on Mars would receive about 0.67 millisieverts of radiation per day, roughly 40 times the radiation exposure people experience on Earth. Over a year, that's about 240 millisieverts, well above the annual limits for radiation workers on Earth. Long-term exposure at those levels significantly increases cancer risk. A mission to Mars and back, lasting 2 to 3 years, would expose astronauts to radiation doses that could increase their lifetime cancer risk by several %. That's not immediately fatal, but it's serious. But here's what's strange. When scientists analyzed the radiation data more carefully, they found variations that don't match our models. The radiation flux changes in ways we can't fully explain through solar activity alone. There are dips and spikes that suggest something on or beneath Mars's surface is affecting the radiation environment. One hypothesis involves subsurface ice. Water, even frozen water, is an excellent radiation shield. Areas with thick layers of subsurface ice show lower surface radiation levels. If you wanted to build a habitat on Mars, you'd want to build it in a location with abundant subsurface ice, not just for water resources, but for radiation protection. But the radiation variations go beyond what we'd expect from ice distribution. There are patterns that suggest magnetic anomalies in the crust might be providing localized protection. Remember, Mars lost its global magnetic field billions of years ago, but certain regions of the crust are strongly magnetized, remnants of that ancient field. These magnetic anomalies create mini-magnetospheres that could deflect some cosmic rays. If we could find these magnetically protected regions, they'd be prime locations for human settlements. Natural radiation shelters, where humans could live with significantly lower radiation exposure. We're mapping these regions now, but the data is incomplete. We don't have high-resolution magnetic field maps of the entire planet. We're extrapolating from orbital data and limited surface measurements. When humans finally land on Mars, one of the first priorities will be to verify these magnetic anomalies and assess whether they really provide the protection we hope they do. Let me tell you about Mars's polar caps. They're beautiful in a stark, alien way. The northern cap is primarily water ice, about 2 miles thick in the center. The southern cap is a mixture of water ice and dry ice, carbon dioxide frozen solid at temperatures reaching -195 degrees Fahrenheit. But these caps aren't static. They're dynamic, constantly changing. During summer, the dry ice sublimes, revealing the water ice beneath. During winter, the atmosphere's carbon dioxide freezes out, building up the dry ice layer again. The caps grow and shrink with the seasons, breathing with Mars's yearly cycle. And there's something strange about the southern cap. It's not symmetrical. The dry ice deposits are thicker on one side than the other, creating an asymmetric cap that doesn't match what we'd expect from a simple seasonal cycle. Some scientists think this asymmetry is caused by prevailing winds that redistribute dry ice across the cap. Others think it might be related to variations in solar heating due to Mars's elliptical orbit. But there's another hypothesis, and it's unsettling. What if the asymmetry is evidence of something beneath the ice? A geological feature, perhaps, or a subsurface heat source that's melting ice on one side of the cap more than the other. We know there's liquid water beneath the southern cap. That lake I mentioned earlier. Could there be more lakes? Could there be a network of interconnected liquid water bodies beneath the polar ice, creating a hidden hydrosphere? If so, that would be a game changer for astrobiology. Stable liquid water environments, protected from radiation and temperature extremes, insulated by miles of ice. Those would be prime habitats for life. Not just microbial life, but potentially more complex organisms adapted to this extreme environment. On Earth, we found life beneath ice sheets, in subglacial lakes, in the interface between ice and rock, even inside the ice itself, feeding on organic compounds trapped during formation. If life exists beneath Mars's polar ice, it could be similarly diverse and resilient. But accessing those environments would be incredibly challenging. Drilling through 2 miles of ice on another planet is no small feat. It would require advanced technology, significant power sources, and meticulous contamination control to avoid introducing Earth life into a pristine Martian ecosystem. Those missions are being planned, but they won't happen for decades. Until then, the secrets beneath Mars's polar caps remain locked away, tantalizingly out of reach. Let me tell you about the Valles Marineris. This is a canyon system that dwarfs anything on Earth. If you placed it on Earth, it would stretch across the entire United States, from New York to California. It's about 2,500 miles long, up to 120 miles wide, and in places nearly 5 miles deep. The Grand Canyon could fit inside some of its side canyons. We think Valles Marineris formed billions of years ago when Mars's volcanic Tharsis region was uplifting, creating enormous stresses that fractured the crust. Water and ice likely played a role in widening the canyons through erosion and collapse. But here's what's fascinating. Valles Marineris might be one of the best places to search for past or present life on Mars. Why? Because those canyon walls expose billions of years of Martian geological history. Layers upon layers of rock, each representing a different era, a different climate regime. And some of those layers were deposited when Mars was warm and wet, when liquid water flowed across the surface. Perseverance and Curiosity are exploring ancient lake beds, which is great, but they're sampling relatively small areas. Valles Marineris offers something different, a vertical cross-section of Mars's entire history, all in one location. Scientists have identified clay-rich deposits in the canyon walls. Clays form in the presence of water, and they're excellent at preserving organic molecules. If life existed on Mars, the canyon walls might contain fossils, chemical biosignatures, or even preserved microbial mats. But accessing those canyon walls is extremely difficult. The canyon floors are treacherous terrain for rovers. Many areas are too steep or too rocky to navigate safely, and the most interesting layers are often high up on the canyon walls, out of reach from the floor. Future missions might use drones or climbing robots to access these deposits. NASA's Ingenuity helicopter proved that powered flight is possible on Mars, despite the thin atmosphere. More advanced aerial vehicles could survey the canyon walls, identifying targets for detailed study. Human explorers could rappel down those walls, collecting samples directly. They could establish camps at different levels, systematically working their way through the geological record. That kind of hands-on exploration would be vastly more effective than anything we can do robotically. But until humans arrive, Valles Marineris remains largely unexplored. Its secrets are visible from orbit but frustratingly out of reach. Now let me tell you about something that's going to make you question everything we think we know about Mars. In 2004, the Mars Express orbiter detected methane in Mars's atmosphere. As I mentioned earlier, this was huge because methane is a potential biosignature. But the story gets stranger. In 2009, scientists reported that methane concentrations varied by location. Some regions had significantly higher levels than others, and the methane seemed to be coming from specific source regions, possibly venting from beneath the surface. The plot thickened in 2013 when Curiosity failed to detect any methane at all when it first started sampling Mars's atmosphere. But then, later that year, it detected a spike. Then the methane disappeared again. The pattern was baffling. Scientists proposed various explanations. Maybe methane is released episodically from subsurface sources. Maybe UV radiation breaks it down quickly, so it doesn't persist in the atmosphere. Maybe there are seasonal variations we don't understand. But in 2019, a team of researchers proposed something radical. They suggested that the methane variations might be too rapid to explain through geological or atmospheric processes alone. They calculated that methane is destroyed in Mars's atmosphere on timescales of hundreds of years. Yet the variations they observed occurred over days or weeks. How can methane concentrations change that rapidly unless something is actively producing it in real time? And the only process we know that can produce methane that quickly is biological metabolism. Now, before you get too excited, other researchers have pushed back on this interpretation. They've proposed alternative mechanisms involving perchlorate reactions that could destroy methane faster than previously thought. They've suggested that methane might be trapped in subsurface ice and released in sudden bursts when ice cracks or sublimates. The debate is ongoing. But here's the point: we have methane on Mars. We don't know where it's coming from. We don't fully understand its behavior. And the possibility that it's biological remains on the table. That should excite you, and it should terrify you, because if there's life on Mars producing methane right now, then we're not just looking at a dead planet with ancient fossils. We're looking at a living planet with an active biosphere that's managed to survive for billions of years in conditions that would kill anything we know on Earth. Let me tell you about Mars's seasons. A Martian year is 687 Earth days, almost twice as long as an Earth year. And because Mars's axis is tilted at about 25 degrees, Similar to Earth's 23.5-degree tilt, Mars experiences seasons just like we do. But there's a crucial difference. Mars's orbit is much more elliptical than Earth's. At its closest approach to the Sun, perihelion, Mars receives about 40% more solar energy than at its farthest point, aphelion. This creates extreme seasonal variations. Southern Hemisphere summer occurs when Mars is closest to the Sun, making it short and intense. Northern Hemisphere summer occurs when Mars is farthest from the Sun, making it long and mild. The result is that Southern Hemisphere seasons are more extreme than Northern Hemisphere seasons. This asymmetry has profound effects on Mars's climate. The southern polar cap partially sublimits during summer, releasing huge amounts of carbon dioxide into the atmosphere. This drives powerful winds that can trigger the planet-wide dust storms I mentioned earlier. But here's what's interesting from an astrobiology perspective. The seasonal variations create transient habitable conditions in certain locations. During summer, equatorial and mid-latitude regions can reach temperatures above the freezing point of water, at least during the day. If there's subsurface ice near the surface, it might melt, creating temporary liquid water. These transient melting events wouldn't last long, maybe a few hours each day during peak summer. But that might be enough for extremophile microorganisms to metabolize, reproduce, and then enter dormancy when conditions turn hostile again. On Earth, we have organisms that do exactly this. Tardigrades, for instance, can survive complete desiccation, entering a state of suspended animation for years or even decades, then rehydrate and resume normal activity when water becomes available again. Could Martian microorganisms have evolved similar survival strategies? Could they be lying dormant in the soil, waiting for those brief summer melting events to come back to life? We don't know, but it's a testable hypothesis. Future missions could target mid-latitude regions and sample the soil during summer, looking for signs of metabolic activity when conditions are most favorable. Now let me tell you about Mars's lost oceans again, but from a different angle. We've established that Mars had a lot of water, but the geography of that ancient water tells us something profound about how the planet evolved. The lowest-lying regions of Mars's northern hemisphere show features consistent with ancient shorelines. These features follow a roughly constant elevation, which is exactly what you'd expect from the edge of an ocean. We can map where the coastline would have been billions of years ago, and when we do, we find that it corresponds to areas where minerals associated with water are concentrated. But here's the mystery. The shoreline isn't smooth. It's irregular, with highlands and lowlands that don't match what we'd expect from a simple ocean surface. Some scientists think this is because Mars's rotation axis shifted after the ocean disappeared, tilting the planet and changing the relative elevations of different regions. If Mars's axis shifted, that would have had catastrophic climate effects. Regions that were once temperate would have become polar. Regions that were once tropical would have frozen. Any life that existed would have had to migrate, adapt, or die. But there's another interpretation. What if the irregular shoreline is evidence that Mars had multiple distinct bodies of water rather than one single ocean? What if there were separate seas, each at different elevations, connected by rivers and straits? That would paint a very different picture of ancient Mars. Not just a wet planet, but a planet with diverse aquatic environments. Shallow seas, deep oceans, brackish estuaries where fresh water from rivers mixed with salty seawater. Different environments would have created different selective pressures, potentially allowing life to diversify and adapt to various niches. If that's true, then the search for life on Mars becomes more complex. We can't just look for one type of organism. We have to consider that there might have been, or might still be, multiple branches of Martian life, each adapted to different environments. Earth's biosphere is incredibly diverse, with organisms adapted to every conceivable niche from deep-sea vents to high-altitude clouds. Why should Mars be any different? If life arose there, it could have been just as diverse, just as adaptable, just as resilient. Let me tell you about Mars's internal structure. Thanks to InSight seismometer, we now have a basic understanding of what's inside the red planet. Mars has a core, mantle, and crust similar to Earth, but the proportions are different. The core is larger relative to the planet's size than Earth's core, occupying about half the planet's radius. The crust is thicker on average, especially in the southern highlands where it can exceed 60 miles in depth. But here's what surprised scientists. The core appears to be entirely liquid, not solid like Earth's inner core, and it's lighter than expected, which means it contains a significant amount of lighter elements like sulfur, possibly hydrogen, and maybe even water dissolved in the molten metal. This has implications for Mars's magnetic field, or rather, its lack thereof. Earth's magnetic field is generated by convection currents in its liquid outer core surrounding a solid inner core. Mars doesn't have that solid inner core, which might be why it couldn't maintain a long-lived magnetic field. But wait, Mars did have a magnetic field once. We know this because certain regions of the crust are strongly magnetized, preserving a record of that ancient field. So what changed? Why did the magnetic field shut off? One possibility is that Mars's core cooled below a critical threshold where the thermal and compositional convection that drives field generation couldn't be sustained. Another possibility is that a massive impact disrupted the core's convection patterns, causing the field to collapse. There's a third possibility, and it's disturbing. What if Mars's magnetic field is still trying to regenerate, but it's too weak to detect with our current instruments? What if there are subtle convection currents in the core that occasionally produce weak, localized magnetic fields? If that's true, Mars might not be as magnetically dead as we think. It might be in a transitional state, occasionally producing weak fields that last for decades or centuries before collapsing again. This matters because magnetic fields protect atmospheres. If Mars had even a weak magnetic field, it would reduce the rate of atmospheric loss to space. It might create conditions where a thicker atmosphere could accumulate over time. And if we're serious about terraforming Mars, about transforming it into a habitable world, we need to address the magnetic field issue. Without one, any atmosphere we create will eventually be stripped away by solar wind, just like the ancient atmosphere was. Some scientists have proposed audacious solutions. We could position a magnetic shield at the L1 Lagrange point between Mars and the Sun, creating an artificial magnetosphere that deflects solar wind. Or we could stimulate Mars's core, restarting convection through some mechanism we haven't figured out yet. These ideas sound like science fiction, but so did landing rovers on Mars once. So did flying a helicopter in the thin Martian atmosphere. Sometimes science fiction becomes science fact. Now let me tell you about Mars's mysterious clouds. You'd think a planet with such a thin atmosphere wouldn't have much in the way of clouds. But Mars surprises us again. Mars has water ice clouds, similar to cirrus clouds on Earth. They're thin and wispy, forming at high altitudes when the sparse atmospheric water vapor freezes into ice crystals. These clouds are most common during spring and summer in each hemisphere. But Mars also has carbon dioxide ice clouds, which form in the extremely cold upper atmosphere. These clouds reflect sunlight and can affect the planet's energy balance, influencing climate in ways we're still trying to understand. And then there are the mystery clouds. In 2012, amateur astronomers observed unusual plumes extending high above Mars's surface, reaching altitudes of up to 150 miles. That's well above the typical cloud formation altitude. In fact, it's so high that it's technically above the atmosphere, in the exosphere where atmospheric density is nearly zero. Scientists were baffled. What could create a plume that high? Dust storms don't reach those altitudes. Water ice clouds don't form there. Carbon dioxide clouds can't explain it either. Some researchers suggested it might be auroras, similar to Earth's northern lights. Mars doesn't have a global magnetic field, but it has localized magnetic anomalies in the crust that could potentially create auroral displays when solar wind particles interact with them. But the plumes didn't match auroral behavior. They were too persistent, lasting for days, and they were too bright to be explained by the typical energies involved in auroral displays. Another hypothesis involved water ice. Perhaps some unusual atmospheric condition allowed water ice to crystallize at much higher altitudes than normal. But the temperatures at those altitudes are so extreme that water ice shouldn't be stable. Here's the disturbing part. We don't have a satisfactory explanation. These plumes remain unexplained. They appeared, they lingered for about 10 days, and then they dissipated. We've been watching for them to reappear, but so far, they haven't. What caused them? Where did they come from? Will they appear again? We don't know. And that's unsettling because it means Mars can still surprise us with phenomena we don't understand, can't predict, and can barely explain. Let me tell you about Mars's crustal magnetism in more detail. As I mentioned, certain regions of Mars's crust are strongly magnetized. These aren't random patches. They're organized into alternating bands of strong and weak magnetization, particularly in the southern highlands. This pattern is eerily similar to the magnetic striping seen on Earth's ocean floors. On Earth, these stripes form as tectonic plates spread apart at mid-ocean ridges. Molten rock rises, cools, and solidifies, locking in the orientation of Earth's magnetic field at that time. When the field reverses, as it does periodically, the next stripe of solidified rock has the opposite magnetic orientation. Does this mean Mars had plate tectonics? That's the implication. The magnetic striping suggests that at some point in Mars's ancient history, its crust was moving, spreading apart in some regions, colliding in others, just like Earth. But we don't see clear evidence of plate tectonics on Mars today. The surface features don't show the kinds of boundaries, subduction zones, or mountain ranges you'd expect from active plate tectonics. Mars appears to have a single, rigid crust rather than multiple tectonic plates. So what happened? Did Mars have plate tectonics early in its history, then stop? If so, why? On Earth, plate tectonics is driven by heat from the interior. As hot mantle rock rises, it drags the crust apart in some places and pushes it together in others. If Mars's interior cooled faster than Earth's, which is likely given its smaller size, the convection currents driving plate tectonics would have weakened and eventually stopped. But here's the fascinating part. If Mars had plate tectonics, even for a relatively short time, that would have had profound implications for habitability. Plate tectonics recycles minerals between the surface and interior, creating diverse geological environments. It regulates atmospheric composition by sequestering and releasing gases. It creates volcanic activity that releases nutrients necessary for life. In other words, plate tectonics might have made Mars habitable. And when it stopped, Mars's climate and habitability might have declined. We're still piecing together this story, but every new piece of evidence suggests that young Mars was far more Earth-like than we ever imagined. It was a dynamic, geologically active world with a thick atmosphere, flowing water, and possibly plate tectonics. It was a place where life could have thrived. The question is, when Mars became less Earth-like, what happened to its biosphere? Let me tell you about the possibility of life on Mars right now. Not ancient fossils, not extinct microbes, but living organisms existing somewhere on the planet at this very moment. It sounds audacious. Mars is cold, dry, and bathed in radiation. How could anything survive? But consider this: we've found life in Earth's most extreme environments. In the dry valleys of Antarctica, where conditions are remarkably Mars-like, microbes survive by extracting moisture from the atmosphere and metabolizing chemicals in the rocks. In Chile's Atacama Desert, the driest place on Earth, bacteria lie dormant for decades, then spring to life when rare rains arrive. Deep beneath Earth's surface, in mines and boreholes miles down, there's an entire subsurface biosphere feeding on chemical energy rather than sunlight. These organisms break down minerals, extract electrons, and use those electrons to power their metabolism. They don't need oxygen. They don't need organic matter from the surface. They're completely independent of the surface biosphere. If life exists on Mars, it's probably similar to these extremophiles. It's probably underground, where conditions are more stable. It's probably using chemical energy, not sunlight. And it's probably dormant most of the time, activating only when conditions become briefly favorable. The Atacama Desert is a particularly relevant analog. Studies have shown that microbial communities in the Atacama can survive with almost no water for years, then rapidly metabolize and reproduce when moisture becomes available. If Martian microbes evolved similar strategies, they could survive in the Martian soil, waiting for those rare moments when temperature and moisture conditions align. The subsurface biosphere is even more promising. If there are liquid water aquifers beneath Mars's surface, and if those aquifers are connected to chemical energy sources like hydrothermal systems, then life could thrive there. It wouldn't need the surface at all. And here's the most exciting part. We're getting close to being able to test this hypothesis. Future missions will drill deeper into Mars, accessing subsurface ice and potentially liquid water. They'll carry more sophisticated instruments capable of detecting biological molecules even at extremely low concentrations. They'll search for metabolic activity, for genetic material, for any sign that Mars is still alive. When we find life on Mars, if we find it, the discovery will rank among the most significant in human history. It will prove that life is not unique to Earth, that it can arise wherever conditions are suitable, that the universe might be teeming with living worlds. But it will also raise profound questions. Where did Martian life come from? Did it originate independently from Earth life, arising through a separate genesis event? Or is it related to Earth life, seeded by meteorites that traveled between the planets carrying microbial passengers? This second possibility is called panspermia, and it's not as far-fetched as it sounds. We know that meteorites from Mars have landed on Earth. We found them, and we know that some microbes can survive the shock of impact, the cold and radiation of space, and the heat of atmospheric entry. It's possible, even likely, that life has been exchanged between Earth and Mars over billions of years. If Martian life is related to Earth life, that would be fascinating but perhaps a bit disappointing. It would mean we found our cousins, not true aliens. But if Martian life is fundamentally different from Earth life, if it uses different biochemistry, different genetic mechanisms, different metabolic pathways, then we've found proof of a second genesis. We've found proof that the chemistry of life isn't unique to Earth, that it can emerge independently in different environments. That would change everything. It would mean life is probably common in the universe. It would mean that among the billions of planets in our galaxy, countless others might harbor life. It would mean we're not alone, and we've never been alone. Let me tell you about the ethical implications of finding life on Mars. This isn't just a scientific question, it's a moral one. If there's life on Mars, even microbial life, do we have the right to colonize the planet? Do we have the right to terraform it, to transform it into a second Earth? Would doing so constitute genocide against a native Martian biosphere? These aren't hypothetical questions. We're planning human missions to Mars within the next 2 decades. We're actively developing technologies to terraform the planet, to thicken its atmosphere, to warm it, to make it habitable for humans. But what if those efforts destroy Martian life? What if by making Mars habitable for us, we make it uninhabitable for them? Some scientists argue we should leave Mars alone until we fully understand its biosphere. We should establish it as a nature preserve, a protected wilderness where life can be studied without interference. Only after we've thoroughly explored the planet and confirmed whether life exists should we consider colonization. Others argue that humans have a right to expand beyond Earth, that our long-term survival might depend on becoming a multiplanetary species. They point out that Mars is likely already dead or nearly so, and that any surviving life would be confined to isolated subsurface pockets that could be protected even as we colonize the surface. There's also a practical consideration. Every mission to Mars carries Earth microbes. Despite our best sterilization efforts, it's impossible to completely eliminate all microbial contamination. With every rover, every lander, we're introducing Earth life to Mars. If there's native Martian life, we might have already contaminated it. This is called forward contamination, and it's a serious concern. If Earth microbes establish themselves on Mars, they could outcompete native Martian organisms, driving them to extinction. Or they could interbreed with Martian microbes if they're compatible, creating hybrids that muddy our understanding of Martian biology. We've tried to prevent this. Spacecraft destined for Mars are assembled in clean rooms and subjected to heat sterilization to kill any hitchhiking microbes. But some extremophiles can survive these treatments. We've found bacteria in clean rooms, thriving despite the harsh conditions. If they can survive on Earth, they might survive on Mars. The situation gets even more complicated when we consider human missions. Humans are walking microbial ecosystems. We carry trillions of bacteria on and in our bodies. When astronauts arrive on Mars, they'll inevitably introduce Earth microbes into the Martian environment, despite any precautions. Should we wait to send humans until we've thoroughly searched for Martian life? Should we designate certain regions of Mars as off-limits, protected from human activity? Should we accept that contamination is inevitable and forge ahead anyway? These are questions we need to answer soon, because human missions to Mars are coming, whether we're ready or not. Let me tell you about the Moon versus Mars debate. Some people argue we should focus on the Moon, establishing a permanent presence there before attempting Mars. The Moon is closer, making missions cheaper and safer. Communication delays are minimal, just a couple seconds. If something goes wrong, help from Earth is only a few days away. But here's the problem. The Moon isn't Mars. It doesn't have an atmosphere. It doesn't have water in accessible forms, at least not in most locations. It doesn't have the mineral resources Mars has. And most importantly, it doesn't have the potential for life. Mars is the prize. It's the next step in human expansion beyond Earth. It's the planet where we might find life, past or present. It's the world that could be transformed into a second home for humanity. The Moon is a stepping stone. It's where we can test technologies, develop life support systems, learn how to live off-world before committing to the much longer and more dangerous journey to Mars. But we shouldn't mistake the Moon for the destination. Mars is the destination. And every day we delay getting there is a day we miss the opportunity to answer one of the most profound questions in human history. Are we alone? Let me tell you about the challenges of getting to Mars. It's not just a matter of building a big enough rocket. The physics are daunting. Mars is, on average, about 140 million miles from Earth. But because both planets are orbiting the Sun, that distance changes constantly. At their closest approach, Mars and Earth are about 34 million miles apart. At their farthest, they're over 250 million miles apart. Launch windows, when it's energetically favorable to send a spacecraft to Mars, occur about every 26 months. Miss that window and you wait 2 years for the next one. Travel time depends on the trajectory. The most fuel-efficient path, a Hohmann transfer orbit, takes about 9 months. Faster trajectories are possible but require more fuel. With current propulsion technology, we're looking at 6 to 9 month journeys under the best circumstances. That's a long time to spend in space. Astronauts would face radiation exposure, muscle atrophy, bone density loss, psychological stress from confinement, and myriad other health challenges. And when they arrive, they can't just turn around and come home. They have to wait for Earth and Mars to realign, which takes about 18 to 20 months. That means a minimum mission duration of about 3 years. 9 months there, 18 months on Mars, 9 months back. 3 years away from Earth. 3 years of isolation. 3 years of risk. But it gets worse. A Mars mission isn't just about getting there and back. It's about surviving on the surface. Mars's atmosphere is 95% carbon dioxide. The pressure is less than 1% of Earth's. Temperatures range from a relatively balmy 70 degrees Fahrenheit at the equator during summer days to minus 225 degrees Fahrenheit at the poles during winter nights. You can't breathe the air. You can't walk around without a spacesuit. If your habitat loses pressure, you have seconds to get to a safe environment before you lose consciousness. Water is locked up as ice or hidden in subsurface aquifers. You can't just drill a well and pump water to the surface, not easily. You'd need sophisticated equipment to extract, purify, and store water. Food is another challenge. You can't grow crops in Martian soil, at least not without extensive modification. The soil contains perchlorates, which are toxic to plants and humans. You'd need to wash and process the soil before attempting agriculture. And even then, you'd need a controlled environment with Earth-like air, temperature, and pressure. Energy is critical. Solar panels work on Mars, but they're less efficient than on Earth because Mars receives only about 43% of the solar energy Earth gets. Dust storms can cover solar panels, blocking sunlight for weeks or months. You'd need backup power systems, possibly nuclear reactors, to ensure continuous energy supply. Every resource you need to survive, air, water, food, energy, has to be produced locally or brought from Earth at enormous expense. A single kilogram of payload to Mars costs tens of thousands of dollars using current launch systems. The challenges are immense, but they're not insurmountable. We have the technology to send humans to Mars. What we lack is the political will and financial commitment to actually do it. Let me tell you about Mars Direct, a mission architecture proposed by engineer Robert Zubrin in the 1990s. It's elegant in its simplicity and audacious in its ambition. The basic idea: send cargo missions to Mars ahead of the crew. These missions would include a return vehicle, a habitat, supplies, and a small nuclear reactor for power. The return vehicle would carry equipment to produce propellant from Mars's atmosphere, using the Sabatier reaction to convert carbon dioxide and hydrogen into methane and water. By producing propellant on Mars, you eliminate the need to carry it from Earth, dramatically reducing launch mass and cost. The crew launches only after the propellant production is complete and verified, reducing risk. When the crew arrives, their habitat and supplies are already waiting. They spend 18 months on Mars, conducting science, exploring, setting up infrastructure. Then they use the locally produced propellant to return home. Meanwhile, another cargo mission has already launched, setting up for the next crew. Over time, you build up infrastructure, creating a permanent human presence on Mars. Mars Direct was never implemented, but it influenced subsequent mission concepts. NASA's current plans for Mars exploration incorporate many of its ideas, particularly in situ resource utilization, using Martian resources to support human missions. But we're still decades away from actually doing it. NASA aims for human missions to Mars in the 2030s or 2040s. Private companies like SpaceX have more aggressive timelines, but they face the same technological and financial challenges. The question isn't if we'll send humans to Mars, but when, and whether we'll do it before we discover what Mars's mysteries might reveal about life in the universe. Let me tell you about Martian caves. Mars has thousands of them scattered across the planet. We've identified them from orbit as dark spots on crater walls and volcanic slopes, openings that lead into underground voids. These caves are fascinating for several reasons. First, they're natural shelters. The thick rock above provides radiation shielding, protection from temperature extremes, and shelter from dust storms. A human habitat inside a Martian cave would be far safer and more stable than anything built on the surface. Second, caves might harbor ice. On Earth, many caves in cold climates contain ice deposits that persist year-round. If Martian caves have ice, they'd be prime locations for human settlements. Water is the most critical resource for long-term survival. Third, and most intriguing, caves are potential habitats for current Martian life. On Earth, cave ecosystems are often isolated from the surface, developing unique species found nowhere else. If life exists on Mars, caves would be among the best places to look. But we haven't explored any Martian caves yet. Rovers can't navigate the steep, rocky entrances. We'd need specialized robots, cave crawlers, or drones capable of flying in low light and tight spaces to investigate these environments. Or we'd need humans. Speleology, cave exploration, is something humans excel at. We can adapt to unexpected conditions, make real-time decisions, and navigate complex three-dimensional environments in ways robots can't match. When humans reach Mars, cave exploration will be a priority. Those dark openings might hold answers to the planet's greatest mysteries. They might reveal preserved ice from Mars's ancient past, offering clues to past climate. They might contain fossilized remains of ancient life. They might even harbor living organisms, the last survivors of Mars's lost biosphere. Let me tell you about the ethical issues of planetary protection in reverse. We've talked about forward contamination, preventing Earth life from contaminating Mars. But what about backward contamination? What if Martian microbes, if they exist, are brought back to Earth? This is a serious concern. Any sample return mission from Mars must ensure that Martian material is completely contained and sterilized before it comes into contact with Earth's environment. The risk of accidentally releasing an alien pathogen, even a microbial one, into Earth's biosphere is unacceptable. But here's the paradox. To study Martian samples properly, we need to keep them pristine. Sterilization might destroy the very biosignatures we're looking for. We need to study Martian material in its natural state to determine if it contains life. The solution is biocontainment. Sample return missions will bring Martian material back in sealed containers that are never opened on Earth. Instead, the samples will be transferred directly to a high-security biocontainment facility where they can be studied in complete isolation. These facilities would be far more secure than anything currently used for studying dangerous pathogens on Earth. Multiple layers of containment, air filtration systems, negative pressure rooms, and protocols to ensure that absolutely nothing escapes. Only after samples have been thoroughly analyzed and confirmed to be sterile would they be released for broader study by the scientific community. This might sound like overkill. Mars is a dead planet, right? There's probably no life there, and even if there is, it's probably harmless to Earth organisms. But we can't take that chance. The consequences of being wrong are too severe. An invasive Martian microbe could potentially devastate Earth's ecosystems, outcompeting native species or causing diseases we have no immunity to. It's unlikely, but the risk isn't zero. And when the stakes are the entire biosphere of Earth, even infinitesimal risks must be taken seriously. Let me tell you about Mars's two tiny moons again, but from a different angle. Phobos and Deimos aren't just interesting because of their mysterious origin. They're strategic assets for Mars exploration. Phobos orbits so close to Mars that it completes an orbit every 7.6 hours. That means it rises in the west and sets in the east, the opposite of what we see from Earth with our moon. From the surface of Mars, Phobos would appear to zip across the sky, rising and setting multiple times a day. This proximity makes Phobos an ideal staging area for Mars missions. A base on Phobos would have several advantages over a surface base. First, you're already partway out of Mars's gravity well, making it easier to launch back to Earth. Second, you have a much wider view of Mars's surface, allowing you to survey large areas and identify interesting targets for exploration. Third, you avoid many of the hazards of the surface: dust storms, perchlorates in the soil, and higher radiation levels. From a Phobos base, you could teleoperate rovers on Mars's surface with almost no communication delay. The round-trip light time is mere seconds, allowing real-time control. That would make surface exploration far more efficient than operating rovers from Earth with delays of 20 minutes or more. You could also use Phobos as a fuel depot. If Phobos contains water ice, and some observations suggest it might, you could extract that ice, electrolyze it into hydrogen and oxygen, and use it as rocket propellant. That would eliminate the need to bring all your propellant from Earth. Some mission planners have proposed that the first human mission to Mars shouldn't land on the surface at all. Instead, astronauts would orbit Mars, perhaps with a stop at Phobos, teleoperate rovers and drones to explore the surface, and return to Earth without ever setting foot on Mars. It sounds less ambitious than a surface landing, but it might be a smarter approach. It's lower risk, easier to pull off with current technology, and still allows for significant scientific return. And it sets the stage for later surface missions. Astronauts would have scouted Mars from orbit, identified the best landing sites, tested equipment and procedures. When humans finally land, they'd be better prepared. Now let me tell you about something truly eerie: Mars's lost magnetic field and the implications for life. When Mars's magnetic field collapsed, it wasn't a sudden event. It declined gradually over hundreds of millions of years. During that decline, Mars's atmosphere was slowly stripped away. The planet cooled. Water evaporated or froze. Any life on the surface would have faced increasingly harsh conditions. But here's the thing: life is adaptable. On Earth, organisms have survived multiple mass extinction events. They've adapted to changing climates, to asteroid impacts, to volcanic eruptions that nearly sterilized the planet. If life existed on Mars during the magnetic field collapse, it didn't just give up and die. It adapted. It migrated to more favorable environments. It evolved survival strategies. The most obvious refuge would be underground. As the surface became uninhabitable, life would have retreated into the subsurface where conditions remained stable. Temperature variations are minimal deep underground. Radiation doesn't penetrate thick rock layers, and there's potentially still liquid water in deep aquifers. This creates a chilling scenario. Mars's surface is dead, but beneath it, there's a thriving biosphere that's been evolving in isolation for billions of years. What would that life look like? It would be adapted to complete darkness, feeding on chemical energy rather than sunlight. It would be slow-growing, metabolizing at rates far below what we see in Earth organisms. It might be dormant most of the time, activating only when conditions briefly allow. And it would be completely alien, not just in the sense of being from another planet, but alien in its fundamental biology. Billions of years of independent evolution would have produced organisms with biochemistry, genetics, and physiology unlike anything on Earth. Finding that biosphere would be the discovery of the millennium, but it would also be terrifying, because we'd have to confront the reality that we've been living next to an entire alien ecosystem and we never knew it. Let me tell you about Mars's ancient impact history. The planet's surface is heavily cratered, preserving a record of billions of years of bombardment by asteroids and comets. Some of these impacts were catastrophic. The Hellas Basin in the southern hemisphere is one of the largest impact craters in the solar system, about 1,400 miles across and 5 miles deep. The impact that created it would have been apocalyptic, releasing energy equivalent to millions of nuclear weapons. Such impacts would have vaporized vast amounts of rock and water, launching material into space. Some of that material would have fallen back to Mars, but some would have escaped the planet's gravity entirely. And here's where it gets interesting. Some of that ejected material would have made its way to Earth. We found meteorites from Mars on Earth. They're rare, but they exist. Scientists identify them by comparing their composition to rocks analyzed by Mars rovers. If Martian rocks can reach Earth, then Martian microbes could too. Microorganisms trapped in rock ejected by an impact would be protected from space radiation and extreme temperatures. Some bacteria form spores that can survive for millions of years in dormancy. It's plausible that living microbes from Mars have reached Earth throughout history. This has profound implications. If Earth life originated from Mars, seeded by impact-ejected rocks carrying microbes, then we're all Martians. Our entire biosphere might have Martian origins. This sounds like science fiction, but it's a legitimate scientific hypothesis called lithopanspermia. Some researchers think it's actually more likely that life began on Mars and spread to Earth than that it originated on Earth. Why? Because Mars is smaller and would have cooled faster after the solar system's formation. Conditions suitable for life might have emerged on Mars before they did on Earth. And during the late heavy bombardment, a period about 4 billion years ago when the inner solar system was pummeled by asteroids and comets, countless impacts would have launched Martian material toward Earth. If life began on Mars first, then seeded Earth, that would be a stunning reversal of our assumptions. We think of Mars as the dead planet and Earth as the living one. But Mars might be the birthplace of all Earth life. Testing this hypothesis requires finding life on Mars and comparing its biochemistry to Earth life. If they're similar, that suggests a common origin. If they're different, they likely arose independently. Let me tell you about Mars's future. Not the distant future when the Sun expands into a red giant and engulfs the inner planets, but the near future, the next few hundred years. In a best-case scenario, humans establish a permanent presence on Mars within the next few decades. We build habitats, greenhouses, and industrial facilities. We extract water from ice deposits, produce propellant from the atmosphere, and manufacture building materials from Martian regolith. Over time, the population grows. What starts as a scientific outpost becomes a settlement, then a colony, then a self-sufficient civilization. Mars becomes humanity's second home. But it won't be easy. The challenges are immense, not just technological but social and political. Who governs Mars? Who owns Martian resources? What happens when Martian colonists decide they don't want to follow Earth's rules? History offers precedents. When European colonists settled the Americas, they eventually declared independence from their home countries. Will Martian colonists do the same? Will there be a Martian Declaration of Independence, a war between Earth and Mars? It sounds far-fetched, but it's worth considering. Human nature doesn't change just because we move to a different planet. People will bring their ambitions, conflicts, and desire for self-determination with them. There's also the question of terraforming. Should we attempt to transform Mars into an Earth-like world? It's theoretically possible. We could thicken the atmosphere by releasing greenhouse gases, warming the planet and causing frozen carbon dioxide at the poles to sublimate into gas. We could introduce photosynthetic organisms to produce oxygen. Over centuries or millennia, we might create a breathable atmosphere. But should we? If there's native Martian life, even microbial life in isolated subsurface pockets, terraforming could destroy it. Do we have the right to make that choice? Some argue that Mars is already dead or nearly so, and that transforming it into a habitable world would be a net positive for life in the universe. Better a living Mars with Earth-derived ecosystems than a dead Mars with nothing. Others argue that Mars has intrinsic value as it is, that we should preserve it as a natural wilderness, a place to study planetary evolution and search for life without human interference. These aren't questions with easy answers. They're moral and philosophical dilemmas that we'll have to grapple with as we expand beyond Earth. Let me tell you about the psychological challenges of Mars exploration. The isolation alone is staggering. The nearest humans are millions of miles away. Communication delays mean you can't have a real-time conversation with anyone on Earth. If you send a message, it takes anywhere from 3 to 22 minutes to reach Earth, then another 3 to 22 minutes to get a response. You're truly on your own. If something goes wrong, help isn't coming. You have to solve problems yourself with whatever resources you have on hand. Studies of isolated environments on Earth, like Antarctic research stations and submarine crews, provide some insights. People can adapt to isolation, but it takes a psychological toll. Conflicts arise. Morale fluctuates. Some people thrive in isolated environments. Others struggle. NASA is studying these issues, conducting analog missions in isolated locations to understand how crews cope with confinement and separation. They're developing selection criteria to identify people who are psychologically suited for long-duration Mars missions. But there are unknowns. No one has spent years in deep space. We don't fully understand the long-term psychological effects of seeing Earth as a tiny blue dot in the black of space, of knowing you can't go home for years, of living in a small habitat with the same few people day after day. There's also the issue of purpose. On Earth, even in isolated environments, people know their isolation is temporary. They have a return date. But on Mars, especially if you're part of a permanent colony, there might not be a return date. Mars might be your new home forever. How do you cope with that? How do you maintain hope and motivation when you know you might never see Earth again? Never breathe fresh air without a spacesuit? Never feel rain on your face? These are profound questions, and they matter because Mars missions won't succeed based on technology alone. They'll succeed or fail based on the people, their resilience, their adaptability, their ability to maintain mental health and social cohesion in the most challenging environment humans have ever faced. Now let me bring this full circle. Let's talk about what Mars means for humanity's future, for our understanding of our place in the universe. Mars is more than a planet. It's a mirror. It shows us what Earth could become. Mars was once warm and wet, potentially habitable. Then it lost its magnetic field, its atmosphere evaporated, and it became the cold, dry world we see today. Earth could follow a similar path. Not tomorrow, not in our lifetimes, but eventually. If Earth's magnetic field weakened significantly, if our atmosphere were gradually stripped away, we could end up like Mars. That's why understanding Mars is so important. By studying Mars's climate history, we learn about planetary evolution. We learn what makes a planet habitable and what causes habitability to fail. That knowledge helps us understand how to protect Earth and how to recognize habitable worlds around other stars. But Mars also represents hope. If life arose on Mars independently from Earth, that means the origin of life isn't a one-time fluke. It means life might be common in the universe. It means that among the trillions of planets in our galaxy, countless others might harbor life. And if we can establish a permanent human presence on Mars, if we can learn to live on a world that's hostile to life as we know it, then we've proven that humanity isn't confined to one planet. We've taken the first step toward becoming a multiplanetary, perhaps eventually an interstellar species. That's the promise of Mars. Not just scientific discovery, not just adventure, but survival and expansion. A future where humanity is no longer vulnerable to a single catastrophe, where we've spread beyond Earth and established ourselves in multiple locations, resilient and enduring. But we're not there yet. We're still at the beginning of Mars exploration. We've sent robots, we've flown drones, we've studied it from orbit. But we haven't set foot there. We haven't established permanent habitats. We haven't proven we can survive on another world. The next few decades will be critical. The decisions we make now, the missions we fund, the technologies we develop, will determine whether humanity becomes a multiplanetary species or remains confined to Earth. And the discoveries we make on Mars, whether we find ancient fossils, living microbes, or a sterile planet, will shape our understanding of life's place in the cosmos. Here's what we know for certain: Mars has mysteries, deep mysteries, questions that we can barely articulate, much less answer. And those mysteries are calling to us, drawing us across millions of miles of space, compelling us to explore, to discover, to understand. Some of those mysteries are scientific. Where did Phobos and Deimos come from? What caused Mars's magnetic field to collapse? Is there liquid water beneath the surface? Are there living organisms hiding in subsurface aquifers or polar ice? Some are philosophical. If we find life on Mars, what does that mean for our understanding of life's origins? If Mars is truly dead, does that teach us something about the fragility of life? If we choose to colonize Mars, are we explorers fulfilling humanity's destiny, or invaders disrupting a pristine wilderness? These aren't easy questions, but they're worth asking, because in seeking answers, we learn not just about Mars, but about ourselves. Mars has haunted humanity for millennia. Ancient civilizations saw it as a harbinger of war, a blood-red wanderer in the night sky. Medieval astronomers charted its movements, laying the foundations for modern celestial mechanics.
Science-fiction writer imagined Martian civilisation, Mars invasion, Mars colonie.
And now, finally, we're beginning to understand Mars for what it truly is. Not a god, not a fiction, but a real place with real history, real geology, and possibly real life. Every image from Mars, every data point, every discovery adds another piece to the puzzle. and the picture emerging is stranger and more wonderful than we imagined. Mars isn't just a dead rock. It's a time capsule preserving evidence of a planet's birth, evolution, and transformation. It's a laboratory where we can study planetary processes that shaped Earth. It's a potential refuge for humanity's long-term survival. It's possibly the home of life that evolved independently from Earth, alien biology waiting to be discovered. And it's close. Cosmically speaking, Mars is right next door. Of all the planets in the universe, of all the potentially habitable worlds scattered across the galaxy, Mars is the one we can actually reach with current technology. It's the one where we can test our theories, explore in person, and potentially establish a new branch of human civilization. That makes Mars precious, not just as a scientific target, but as an opportunity to expand, to learn, to survive, to thrive. But opportunities don't last forever. The window for Mars exploration is now. We have the technology. We have the knowledge. What we need is the will to do it, the commitment to fund missions, to take risks, to push the boundaries of what's possible. If we seize this opportunity, the rewards could be extraordinary. If we let it slip away, focusing on nearer-term concerns, avoiding the costs and risks, future generations will look back and wonder why we didn't act when we had the chance. The mysteries of Mars are waiting. They've been waiting for billions of years. They'll wait a bit longer if necessary, but we shouldn't make them wait, because every day we delay is a day we don't have answers, a day we remain ignorant of truths that could reshape our understanding of life, of planets, of our place in the universe. Mars is calling. Are we brave enough to answer? Standing here at this moment in history, we're closer to answering the fundamental questions about Mars than ever before. Our rovers are drilling into ancient lake beds. Our orbiters are mapping subsurface water. Our scientists are analyzing data that might contain evidence of life. But the greatest mysteries remain unsolved. We don't know if life exists on Mars now. We don't know if it existed in the past. We don't know where Phobos and Deimos came from. We don't fully understand the planet's climate history, its magnetic field collapse, or the fate of its ancient oceans. What we do know is that Mars has the power to surprise us. Every mission reveals something unexpected. Every data set contains anomalies we struggle to explain. Mars keeps its secrets close, revealing them slowly, one tantalizing clue at a time. And that's what makes it so compelling. Mars isn't just a scientific problem to be solved. It's a mystery to be unraveled, layer by layer, revelation by revelation. The shivers you feel when contemplating Mars aren't from cold, though Mars is certainly cold. They're from awe, from the realization that we're living in an era when we can actually explore another world, when we can search for alien life, when we can expand beyond Earth. Our ancestors looked up at Mars and saw a red point of light, mysterious and unreachable. We look up and see a destination, a world we can visit, explore, and perhaps one day call home. That transformation from mystery to destination is ongoing. We've learned so much, but there's so much more to discover. Every answer generates new questions. Every solved mystery reveals deeper mysteries beneath. Mars has been patient. It's been waiting for billions of years for someone to arrive and read the story written in its rocks, its ice, its thin atmosphere. Now we're here beginning to read that story. And what a story it is. A story of a world that was warm and wet, that might have harbored life, that transformed into a frozen desert. A story of rivers that carved valleys, oceans that covered lowlands, volcanoes that built mountains. A story that mirrors Earth's history in some ways and diverges dramatically in others. We're privileged to be the generation that's uncovering this story. We're the first humans to see the Martian surface in high definition, to analyze Martian rocks, to fly aircraft in Martian skies. We're the pioneers of Mars exploration, and the legacy we leave will shape how future generations view the red planet. Will we find life? Maybe. The evidence is suggestive but not conclusive. We need to look deeper, drill farther, search more thoroughly. Will we establish permanent colonies? Possibly. The challenges are immense, but humans have overcome immense challenges before. Will we terraform Mars, transforming it into a second Earth? Perhaps, though that decision carries profound moral implications we're only beginning to grapple with. What's certain is that Mars will continue to surprise us, to challenge our assumptions, to expand our understanding of what's possible. The mysteries that send shivers down your spine, the secrets hidden beneath red dust and polar ice, the possibilities of life past or present, these aren't abstractions. They're real. They're waiting on a real world that orbits our sun, a world we can see in the night sky, a world we can reach. Mars isn't Mars of mythology. It's not Mars of science fiction. It's Mars of reality, and reality is stranger and more wonderful than any fiction. So look up tonight, find that red point of light, and remember, you're looking at the next chapter of human exploration. You're looking at mysteries that might redefine our understanding of life in the universe. You're looking at a world that was once Earth-like and might be again. You're looking at Mars, and Mars is looking back, waiting for us to uncover its secrets. The journey has only just begun.